Today we're talking about medians and altitudes of triangles. And these are going to be more lines that we draw on the inside of a triangle. And so it's going to be really important that you have examples of both these and of the ones that we did yesterday. And you will find a really nice table on page 339 in your book. Okay, and so your best bet is going to be to write those down in there and then make extra notes. Okay, on the side. So if it was me, I would copy down the table on page 339, and then I would make extra notes, like I'd leave extra room as we talk about each of those. That's just my thought on that. So first, today we're going to talk about a median. And a median is going to be a line segment whose endpoints are the vertex of a triangle and the midpoint of the opposite side. So if we have a triangle here, okay, and I want to draw a median, okay, the median has to start at a vertex, and it has to go to the midpoint of the opposite side. And we're going to know that that point on the opposite side is a midpoint either because they will label it with tick marks or they will give you measurements of that opposite side. So they might say, you know, each of these sides is 5 units long or something like that. Or they might use the tick marks. It's their choice. Okay. And so this line segment that we have created then is called a median. Now, some of you are thinking, how is this different than the perpendicular bisectors that we created yesterday? And the key is going to be that these angles down here do not have to be right angles. In fact, a lot of times they will not be right angles, and a lot of times they will not actually be the same angle measurement on either side of the median. Another key is a perpendicular bisector does not have to go through a vertex. Okay, so a median has to go through a vertex, and it has to go to the midpoint of the opposite side. Okay. Now, if you draw a median from every vertex to the opposite side, then you are going to get 3 lines that intersect, and they are going to intersect at what's called the centroid. The centroid, definition of a centroid, is going to be the point of concurrency of the 3 medians of a triangle. It's also the center of gravity for a triangular region. So if any of you have ever played with like the little eagles where you can balance them on your finger, you know, right on their beak, that's actually using this idea of a centroid. So you're going to see in our example here, we have triangle ABC, and I've drawn the 3 medians. They all start at a vertex and go to the midpoint of the opposite side. And they all intersect here at this point in the center of the triangle. And so this is going to be what's called the centroid of the triangle. Okay, and the root word for this is the same as center because for most purposes of building, things like that, this is really the center of the triangle as far as they're concerned because they're interested in that balancing point. If you are building a triangular table or a stool or something like that, and you only wanted it to have one leg in the center, this would be where it needed to be placed. Okay, and so that's where it's getting its name. We also have a theorem that goes with this called the centroid theorem, and you can find this exact box in your book on page 335. Okay, so again, that's page 335. Right? And so what this is saying is this is how we're actually going to use the centroid to be able to find measurements on a triangle. So you're going to notice that this triangle here that they've given us in the example, triangle ABC, has 3 medians, and it also has our centroid. Point P is the centroid. Okay, so you can see that here in the center. And we are told then that if you have the 3 medians intersecting, and they intersect at the centroids, that from the vertex to the centroid, okay, and that's really important, from the vertex to the centroid, okay, is going to be 2/3 of the total distance of that median, okay? So it's really important. You have to start at the vertex end, and you are going to the centroid, okay? that's the AP here, it is going to equal 2/3 of the whole. So if I was labeling this, and I'm going to draw out my triangle separately, you're going to notice I only drew out the part that I'm interested in for this first little section here. And this is when I tell you that it's sometimes helpful to draw out just the part you want from a problem. This is what I'm talking about. I'm only interested in looking at this one right now. So what I can say here is, since P is the centroid, from the vertex A to P is going to be 2/3 of the total distance. That means that from the centroid to the other endpoint of that line segment, which is the opposite side, midpoint of the opposite side, that's going to be 1/3 of the total distance. Okay, and that's true for each of those medians that's drawn, and it's always going to start at the vertex to the centroid. That's the part that is 2/3. Okay, and we'll look at some examples of how you can use that to solve things tomorrow, but it's going to be really helpful for you to have that labeled in your notes. Okay. Next, we're going to talk about an altitude. And an altitude has to start at a vertex, similar to a median, and it has to make a right angle with the opposite side. So it has to be perpendicular to the opposite side, and that's going to be our most important thing. And what's going to happen here is sometimes that's going to be on the inside of a triangle, like it is in this first triangle here. Sometimes, though, like on our second triangle, and pretty much every obtuse triangle, that altitude actually ends up being drawn on the outside. Okay, and what that means is that we have to extend the side that is opposite vertex B in this case. So when you notice that they have just drawn the little dashed lines here, like they have between C and D, that's just because they are extending that line so that they can show you that your altitude is perpendicular to that opposite side. Okay? And the points where all of the altitudes are concurrent, okay, is going to be called the orthocenter. All right? So the orthocenter is the point where if you draw all three of your altitudes, that's the point that you're going to get. Okay? Now, tomorrow at the beginning of class, we are going to work out several examples about how you can find the centroid of a triangle, how you can find the orthocenter of a triangle, especially if they're given to you, like the vertices of a triangle are given to you on a graph. And so one of the other things I'd like for you to look at tonight is writing the equations of lines. That's going to be back earlier in your notes, earlier in your book. And that's going to be really important because if you can't do that, you're going to have a really hard time just setting up the problems tomorrow. And so just heads up, you want to do that. Also, fair warning, don't be surprised if, on your quiz that's coming up at the end of the week, if you end up with something like that table that I told you might want to write down. Again, that's in your book on page 339. And don't be surprised if I gave you something like this, where you have to go back and you actually have to fill in the missing information, okay? So it's going to be really important that you have your notes filled out and that you can tell which line segment we drew on a triangle, and then if you were to draw all three of those line segments in a triangle, what would that point of concurrency be called? Okay, and we will look at some specific examples in class also, about how these might be used in real life. And you're going to notice that some of your questions in the book also kind of guide you to look at some of how those triangles might be used in real life. So I really appreciate you watching, and I hope you have a wonderful afternoon. Welcome back from the break, and I will see you later. Bye.